Particle in a circle is our first example on a circle. First example of solving the Schrodinger equation. Last time I showed you a particle in a circle and we wrote a wave function and we said, okay, let's see what is the momentum in it. But now let's solve completely this problem. So we have a particle in a circle, which means particle moving here. And this is the coordinate x, and x goes from 0 to L, and we think of this point and that point identified. We actually write this as x is the same as x plus L. This is a strange way of saying things, but it's actually very practical. Here's 2L, 3L. We say that any point is the same as the point in which you add L. So the circle is the whole infinite line with this identification. Because every point here, for example, is the same as this point. And this point is the same as that point. And so at the end of the day, everything is equivalent to this piece where L is equivalent to 0. It's almost like if I was walking here in this room, I begin here, I go there, and when I reach those control panels, somehow it looks like a door, and I walk in, and there's another classroom there with lots of people sitting, and it continues and goes on forever. And then I would conclude that I live in a circle, because I've just begun here and returned to the same point that is there, and just continue. So here it is, you're all sitting here, but you're all sitting there, and you're all sitting there, and just live on a circle. So this implies that in order to solve wave functions in a circle, we'll have to put that psi of x plus L is equal to psi of x. These are the same points. And we'll have zero potential. V of x equals 0. We'll make life simple. So the Hamiltonian is just minus minus h squared over 2m, the second dx squared. Okay. We want to find the energy eigenstate, so we want to find it minus h squared over 2m, the second psi dx squared is equal to E psi. We want to find those solutions. Now, it's simple, or relatively simple, to show that all the energies that you can find are either 0 or positive. It's impossible to find solutions of this equation with negative energies. And we do it as follows. We multiply by dx and psi star, is known psi star, and integrate from 0 to L. So we do that on this equation. And what do we get? Minus h squared over 2m integral psi star of x ddx of ddx psi of x is equal to E, and the integral of psi of x dx. And we will assume, of course, that you have things that are well normalized. So if this is well normalized, this is 1. So this is the energy is equal to this quantity. And look at this quantity. This is minus h squared over 2m. I could integrate by parts. If I do this quickly, I would say just integrate by parts over here. And if we integrate by parts d dx on psi of x, we will get a minus sign, we'll cancel this minus sign, and we'll be over. But let's do it a little bit more slowly. You can put d dx. This is equal to d dx of psi star d psi dx minus d psi star dx d psi dx. I'll do it like this with a nice big bracket. Look what I did. I rewrote the psi star, this second of psi, as d dx of this quantity, which gives me this term when the derivative acts on the second factor. But then it gives you an extra term when the derivative acts on the first factor that is not present in the above line. Therefore, it must be subtracted out. So this bracket has replaced this thing. Now, d dx of something, if you integrate over x from 0 to L, the derivative of something, this would give minus h bar squared over 2m psi star d psi dx evaluated at L and at 0. And then minus cancel, so you get plus h squared over 2m integral from 0 to L dx d psi dx squared equal E. And therefore, this quantity is 0. The point L is the same point as the point 0. This is not the point at infinity. I cannot say that the wave function goes to 0 at L or goes to 0 because you're going to infinity. No, but I have a better argument in this case. Whatever it is, the wave function, the derivative, everything is periodic with L. So whatever values it has at L equals 0, it has at x equals 0, it has at x equals L. So this is 0. And this equation shows that E is the integral of a positive quantity, so showing that E is greater than 0, as claimed. So E is greater than 0, so let's just write a couple of solutions and stop. We'll comment on them more next time, but let's get the solutions, because after all, that's what we're supposed to do. The differential equation is d second psi dx squared is equal to minus 2me over h squared psi. And here comes the thing. We always like to define quantities, numbers. If this is a number and E is positive, this I can call minus k squared psi, where k is a real number. K real. Because k real, the square is positive, and we've shown that the energy is positive. And in fact, this is nice notation, because if you're setting k squared equal to 2me over h squared, you're saying that E is equal to h squared k squared over 2m. So in fact, the momentum is equal to hk, which is very nice notation. So this number k actually has the meaning that you usually associate. that hk is the momentum. And now you just have to solve this. The second side, the x squared, is equal to minus k squared psi. Well, those are solved by sines or cosines of kx. So you could choose sine of kx, cosine of kx, e to the ikx. And this is kind of better or easier because you don't have to deal with two types of different functions. And when you take k and minus k, you reproduce these two. So let's try this. And these are solutions. Indeed, psi is equal to e to the ikx. So we'll leave for next time to analyze the precise details. What values of k are necessary for periodicity and how we normalize this.